Okay, thank you. So lecture 39. We now consider another effect which is just the extreme of the short channel called narrow width effect. So far we have considered only short channel, but the width can also be very small compared to L in certain cases. In that case, if I see the device cross section over the width, it is something like this. This is along the width, that is why I said that earlier, so far we have seen the transistor only over along the channel length. Now we are seeing the MOSFET along the width direction. That is why here there is no junctions present. You just visualize the plan or the top view of the MOSFET. There is a source N plus diffusion, there is a drain N plus diffusion. You are looking at so far you had been looking over the transistor from 0 to L along the channel length. Now you just position it by 90 degree, rotate by 90 degree, and see the cross section along the width. So what you will find there? Over the gate region there is a thin oxide that is called gate oxide, whereas outside it there is field oxide, a thicker oxide. That's how the channel is confined over the width. And what else is done? I have already indicated. For confining the channel along the width direction, along the channel direction, the channel is confined between to N plus and N plus, source and drain. Is it not? When I draw this diagram, the channel is confined from A to D, which is nothing but the source diffusion edge and drain diffusion edge, but perpendicular to the channel, perpendicular to it along the depth. How the channel is confined? It is confined by, firstly, a thin gate oxide is present. That defines the channel along the width, and the remaining thick oxide. And what else is done to define the channel? A channel implant. This is a channel implant. There is a field implant also. Remaining region below the oxide, thick oxide, there is a separate implant that is called field implant. Do you know why this field implant is necessary? Because suppose we take the case of N MOSFET. I told you, if you are not cautious enough, your surface may remain inverted because of the positive QF. If the substrate is p-type, which is the NMOS case, And if the p-type concentration is not high enough, then what is going to happen? Because of QF, positive field oxide charge at the interface of the oxide, electrons will be attracted from the bulk, and inversion layer will be formed even when Vg is equal to 0. And that inversion layer, is it confined over the gate only, or it will be everywhere? Because you are doing the oxidation everywhere. Only over the gate region, the oxide thickness is very small. And the remaining region, it is thick oxide called field oxide. Am I correct? So in that case, the inversion layer, which is naturally formed in the absence of gate bias event, will not be confined only below the to the channel, but also everywhere. So what will happen as a result? All the devices will be connected by the inversion layer. All the MOSFETs, which should otherwise be electrically disconnected, electrically isolated, they will be connected via the inversion layer. And your circuit will not work. You have to do something to remove that inversion layer. What is to be done? Exactly the same thing which you did here to control the threshold voltage. Here you just adjusted this surface implant such that the threshold voltage was the desired value of 1 volt. But in the remaining region, I have to make a situation where inversion layer is very properly, thoroughly removed, and maybe the inversion, the corresponding, it's called field threshold. There is a threshold voltage called field threshold. Okay. Whenever there is a MOS, there is a MOS capacity, there is a threshold voltage. In the field oxide region also metal line is passing. There is an oxide, so MOS capacitor is getting formed. But in that case, even the highest voltage of the gate, whatever metal lines you are using over the circuit, even if you apply the highest possible voltage, under the highest possible voltage also, the channel must never be implanted, must never be inverted. That is called field threshold voltage should be very high. Normally it is a required thing that the actual threshold voltage should be the proper value desired, and the field threshold voltage should be very, very large, and there is some thumb rule. I'm not going for that. And for that, what they do, they normally do an implant over the rest region called field implantation. You have not, I do not know whether the MOS technology has been taught to the MTech, the VLSI technology course, but here is a standard practice that a field implant is carried out to remove the inversion, the presence of inversion layer from the surrounding region. But let us ignore all these things. Let us assume that there is no such, it is an ideal, called flat band case, ideal flat band case. In that case, the only way to define the channel along the transverse direction or the width, that is why I have called it W now. In earlier diagram, this was L, but in this diagram, this is W, and I have assumed W is very small compared to L. Just the extreme, the other extreme. The last lecture it was L very small compared to W. Now W is very small compared. That is why it is called narrow width effect. Then the depletion layer which will be induced under the gate will not be confined only to this region, but it will spread also to the left of A and B like this due to the edge effects, electric field lines, leakage due to the edge effect, due to the edge effect, the potential, the electric field will also, and approximately we can assume that this is a circular, semi-quarter circular region. Approximately, let me tell you, this is not exact, but approximately we can say that the depletion layer boundary beyond C and beyond D, to the left and to the right respectively, is semi-circular or quarter circular as indicated here. So what is going to happen here? This is an interesting thing. When you apply a gate voltage, the charge which is induced is confined not only to the rectangle ACBD just below the width, but also spread to the left and spread to the right as indicated here. So in this case, I can now again define a charge sharing factor which I call F narrow width effect, and that is equal to the area of A dashed C D B dashed, there is the whole thing divided by the area of A C D B rectangle. I am assuming it is uniformly doped. So earlier expressions also valid only for uniformly doped case. For implanted channel, you have to modify it. You can do it yourself for implanted channel. Is it correct? And this is one thing you note, this is greater than equal to 1 instead of less than equal to 1. And this area can be written as D max into W plus half pi D max assuming that these two are quarter circular regions. And that can be written as and please note that this is a very rough approximation. Let me tell you, this model is very rough. Assuming that these two regions will be quarter circular is rather rough. In fact, one has to find out this boundary by solving the 2D Poisson's equation. That will give you a boundary which is more roughly elliptical shaped, not a circular shaped boundary, roughly elliptical shaped boundary. But this gives you simple formula which we prefer. And in that case, you can write your Vt in the same fashion as VFB twice phi f plus f narrow width into 1 upon Ci, the same formula. This is under the approximation that W is small compared to L, or narrow width approximation. And here, because f is more than 1, Vt will be more than Vt dash, the modified Vt will be more than the actual Vt. So you get from curve something like this. This is an interesting thing. When the width is very narrow, threshold voltage increases rather than decreases. Earlier in the, you just compare it with these results. Where channel length is reduced, threshold voltage decreases. But here, when W is reduced, threshold voltage increases. Normally, these narrow width transistors are very not very rarely used nowadays. Earlier, they are used too quite often because you have to maintain a high W by L ratio of the driver with respect to the source, driver with respect to the load. And earlier, L was not a concept because the MOSFETs were meant for slow speed operations, bipolar, very early days, bipolar for high speed. For slow speed, they never bothered about L, the value of L. So they did not mind to make L very small compared to W. And that is the case this. But when you make this, the threshold voltage is altered, as indicated here. Threshold voltage is increased, and this is a very the so-called famous narrow width effect, which is also modeled properly in SPICE. One thing you have not asked me, quantitatively, I have not given any quantitative values here. Here or here, when the so-called narrow width starts, or narrow short channel starts, roughly it is found that this edge is roughly 3 micron. And somewhere here, this thing starts very vigorously. In fact, VT falls quite sharply below 1 micron. In fact, if you go to 0.3 micron, maybe the curve is like this. Similarly here, W, maybe if L suppose is 50 micron, then when W roughly 3 micron, from 3 micron onward it is found that this 3 to 4 micron, max 5 micron is the right line. Normally we say below 5 micron gradually are going to VLSI domain. Above 5 micron it is LSI. So 3 micron we have found from many calculations that below 3 micron all this became of a start gaining importance, and below 1 micron they become very important, very important, very dominant. In fact, all these models below 1 micron they lose their validity. Whatever kind of model which you have developed here, they can be used up to roughly 1 micron. Below 1 micron you have to go for more rigorous models, which is not done here. It is outside the analog domain. Then what else happens when the channel length is reduced? And the one which I have already mentioned called channel length modulation. This is a short channel effect. Why it is a short channel effect? What is that channel length modulation? You remember? 1 second, let me tell you. So I told you, I discussed this very much earlier. When Vg minus Vg become sorry, it is just the opposite. when this thing happens, the VDs become large compared to VG minus VT. That means VG minus effective bias here is less compared to VT. Then near the drain end, the channel become, that inversion does not exist. You say that normally pinch off takes place at this onset of saturation, drain current saturation, the pinch off starts here. As you are increasing the drain bias, the pinch off point gradually starts moving to the left. And this results in an effective channel length reduction, L dash, which is L minus delta L, decreases with increasing bias. As VD increases, L dash decreases. L dash decreases means W by L ratio increases. Therefore, current will increase for the same drain bias. And as a result, the characteristic which I have plotted earlier, the ID-VD characteristic, whereas for the long channel case, the curve is something like this. For the short channel case, the curve for the same gate bias, gate bias or from the same, I should say, for the same gate bias. Can you tell me what will be this is for long channel. This curve is for long channel. ID-VD characteristics for long channel. What will be the expected ID-VD characteristics taking into account the VT lowering with short channel effect, VT lowering as well as the delta L effect, that is the channel length modulation. Due to VT lowering, what will happen? Because VT is reduced, for the same VG, current will be more, isn't it? So the linear region also current will increase. As we enter into the saturation region, delta L is getting gradually increasing. Therefore, the current still fast. So in fact we get a curve, so I think something like this. This is the curve for long channel and this is the curve for short channel. For the same VG is the same for both the curves. Now, the modeling, analytical modeling of the channel length modulation is little difficult, and we are not taking that in this class, in this course, because otherwise I cannot finish the subject. I will come to that while discussing the SPICE models. While discussing SPICE model, I'll bring it that. Otherwise, this modeling, this channel length modulation effect is a big thing. I do not like to incorporate in this class, but only qualitatively I wanted to say that this ID-VD characteristics is the most important thing for your MOSFET, for circuit simulation purpose, is affected by drain-induced barrier lowering, by the short channel charge sharing effect, and thirdly, due to the channel length modulation effect. All of them combined together act behind the, the IDV, the influence combined, in a combined fashion, they influence the current voltage characteristics of a MOSFET. Is it okay? One thing which is also important, we have never discussed, is called VPT, or pass through. We have discussed pass through voltage only for bipolar, but never discussed VPT for, but here also pass-through will take place because when channel length is very small, pass-through is naturally will take place. So if this is the boundary of depletion layer boundary of around a source, then a particular drain bias, the depletion layer boundary of the drain may coincide with this. This may be for a particular drain, and that drain bias is called the pass-through voltage. Somehow, if the depletion layer boundary induced by the drain bias touches the depletion layer boundary induced by the source bias, then what is going to happen? As soon as you apply a gate bias which is close to the threshold, or even slightly less subthreshold region, there is substantial reduction of the barrier at the source end, the current will be very high. There will be no control of gate voltage afterward. So once the pass-through sets in, the device will not function properly. So pass-through voltage is another very, very important parameter for short channel MOSFET, which is otherwise not important for long channel. When 5 micron, 10 micron is the channel length, pass-through never happens. It is breakdown which dominates over pass-through. The junction breakdown dominates over pass-through and not the pass-through. But it becomes important for submicron or deep submicron MOSFETs, where the channel length is less than a micron or 0.5 micron, 0.2 micron kind of channel length. What is to be done to prevent? Because VPT becomes so small that it becomes very your normal power supply voltage is 5 volt or 3 volt. There is a recent trend towards 1.2 volt, 1.1 volt. Otherwise, it's 5 volt or 3 volt. And for the kind of doping normally used, and if you are using a say 0.18 micron CMOS technology or 0.15 micron CMOS technology, it's very popular today. The pass-through will be a tremendously important parameter for the MOSFET. And I have to increase the value of VPT. If I do not increase the value of VPT, it will not work. How can you raise the value of VPT? Yeah, one is using a higher doping. That is normally done. The substrate doping today is usually about the order of 10 to the 17, not 10 to the 15. But that also poses certain problems because that also helps in the early breakdown voltage. Using a higher substrate bias means the substrate concentration in breakdown voltage is reduced. So what people do is, yes, they use a slightly higher substrate concentration and also a dual channel implant. Do you know? They do 2 implants. One is shallow implant at a low energy and a low dose for the control of the threshold voltage. It is followed or preceded by a deeper, slightly higher dose implant. That means 2 implants. Channel implantation is done in 2 stages. One is shallow. Shallow means low energy. Low dose implant, and that is for VT control. Is followed by a deeper, higher energy. Higher dose. Implant, and that is for VPT, for increasing the value of VPT, so that the resulting channel profile looks like this. There is a small peak near the surface. It's a boron implant. Usually it is boron implant for NMOS. There is a small peak near the surface That is the result of the first shallow or low energy, low dose implant. And that is for the control of the threshold voltage. And then a deeper, that means higher energy and slightly higher dose implant is done, so that the peak is positioned a little bit below the surface, and the maximum value, N max value is also higher here compared to the N max of the first peak. So if I now, that expand this, then if this is the plot of N, then actually the curve looks like this. The first peak, just below the surface, this distance may be of the order of 200 angstrom, whereas this distance may be of the order of 800 angstrom or 1000 angstrom. Whereas this N max may be of the order of, say, 10 to the 18. This N max may be even more than that. This may be of the order of 10 to the 17, and whereas this may be of the order of 10 to the 18. The first peak is for the 3T control, but the second implant is for the VPT control. VPT has become a very, very important, it's a matter of concern, which was earlier never considered. Yeah, that is why, that is why if you uniformly dope the whole thing, the breakdown is, an early breakdown is more probable than, that localized, this thing, localized peak implantation. You have to, breakdown is a matter of concern, therefore you have to make a trade-off. Let me tell you, you have to find out the value of V breakdown of this, you have to find out the value of VPT, everything, and come to the next curve. And then you have to have your whole thing so that the 1 volt or 3 volt or 5 volt power supply is quite okay for your devices. It's not only the power supply, there is always a fluctuation tendency. If it is 5 volt, always you have to design for 10 volt. If it is 3 volt, you have to design for 6 volt minimum. If it is 1 volt, you have to design for 2 volts minimum. If you do not do any time, a small fluctuation will result in the breakdown.
So, if doping is not uniform, then the breakdown is lower. Yes. In these two channels, breakdown voltage increase.
If it is uniformly high doped, the breakdown voltage will be reduced. But if it is not uniformly high doped but localized high doped, the breakdown voltage will not be that. It will be reduced definitely, but not that much reduced. You have to do a compromise, and that calculation is not a simple task. The calculation of breakdown voltage, with a non-uniform channel is not a simple task, quite a difficult task. Then it is called drain voltage limitation. You have asked that question. I am just trying to plot a typical value of maximum drain voltage you should apply, that is called limiting value of the drain voltage against channel length, and it's a typical value that I am writing, but this may not be. It all depends on, these values, please remember, all depends on the thickness of the oxide and all those things. Just you don't take these values therefore very rigorously. And just see the nature of the curves. One is a breakdown. The other is called parasitic bipolar effect. I'm coming to that. It is found that as you reduce the L value, the breakdown voltage is also slightly reduced due to the avalanche breakdown voltage is all because combined gate drain source they come in. The big and due to curvature effect, etc. It is found the breakdown voltage of the drain junction is also slightly reduced, as indicated here. You should never go above that. Your drain bias should never be above VBR. This is one thing. Second thing is, as you reduce L, it is found that the subthreshold slope, due to the channel length modulation effect, the subthreshold slope becomes very highly increases, means the subthreshold current becomes too high to be unacceptable. So there is a limit imposed by that. You should be below this. So you should be below this and you should be below this also. Similarly, another thing comes in which is not important. So for a large channel length, this usually the pass-through voltage is very high. You are not bothered about that. But as you reduce this, the pass-through voltage starts falling quickly. So you should be careful. You may have to be remaining in this particular region. So when you use the MOSFET, you design a MOSFET, the maximum drain bias, VDD value in fact, VDD, the design for the VDD is limited by many things. One is the breakdown voltage of the junction. For that, what is the requirement? The substrate doping should be less. The other is the parasitic bipolar effect. And that is automatic to come. How can you get little bit less parasitic bipolar effect? That means the diffusive motion of the carriers have to be reduced. Parasitic bipolar effect is due to the diffusion of carriers which are injected from the source. And that has to be minimized. So how can you do that? Increasing either a higher doping kills lifetime. Okay? Or some kind of trapped, some kind of, that recombination centers introduced to reduce parasitic bipolar effect for the very short channel length. But then as you increase the doping, the pass-through dominates. So you are under the trap. Initially you are under the trap of breakdown voltage, avalanche carrier multiplication, etc. Then the parasitic backward. This is not that serious. In fact, therefore we draw a curve, something intermediate like this. You should be below this line. Between VBR and the parasitic bipolar effect, you can draw a curve, you should be below this. At the same time then, because pass-through voltage was very high, you were not bothered earlier. But now pass-through voltage starts falling. You should be limited, particularly in a region like this. So this is a very complicated picture, and you have to take. That is why people do channel dual implant and various other things for doing that. Another very important effect is, that called hot carrier induced stress. When you know that hot carrier is important for long channel, short channel both. But short channel becomes, do you know why it becomes very important? Because with the channel, as you are decreasing the channel length, the oxide thickness, etc., everything is getting reduced proportionally. When your oxide, the channel length was say 5 micron, the oxide thickness was 1000 angstrom. And when you are using a channel length of 0.18 micron, the oxide thickness has gone down to 150 angstrom. You just see. So therefore, the hot carrier effect becomes important today when you are considering. Otherwise, hot carrier effect was always there. And as soon as you apply a large drain bias or gate bias, the hot carrier effect. What is that hot carrier effect? Let us try to understand. As I told you that when you apply a large drain bias VD, you know that the electric field, actually you know that the typical depletion layer boundary will be something like this. I have plotted so many times. This is a depletion layer boundary, typical. But then because of the large bias, you see that this is what will happen. The peak voltage, the electric field will be very high at the junction plane. What will be the nature of electric field distribution from here to here? If it is uniformly doped, it is a straight linear distribution with a peak at the interface, at the junction. However, if it is graded, there will be a different nature. But always the peak of the electric field will be here. So what will be the direction of the carrier flow? As the electron, you know that there are inversion electrons are here. But as they are going, they will locally go along the directions of the electric field. Electron carriers always flow along the direction of electric field, charge carriers. And what will be the nature of electric field here in this region? One is naturally like this. What will be the direction of electric field? Sorry, it will be like this. But because of the end effect, there will be some fringing field like this, which will penetrate through the oxide, and via the gate it will return to the substrate. You see that this effect is not that important when the gate oxide thickness is large. When gate oxide thickness is very small, gate insulator thickness is very small, then the A effect becomes a very prominent effect, that electric field lines, they not only directly penetrate from the source from the drain to the substrate, but also via the oxide and the gate electrode, they penetrate back into the substrate at the edge. At the edge means at the surface of the drain junction, at the surface side of the drain junction. And remember, these electric field may be quite in excess of about 10 to 20 kilovolt per centimeter. The electric field over this region, Emax, may exceed about 20 kilovolt per centimeter usually exceeds, because it is such a small device, even applying a 3 volt means a very strong electric field. The distances are so small, the electric field usually exceeds that limit of 20 kilovolt per centimeter. So what has happened as a result, these electrons become, they are called hot electrons, because they travel with saturation velocity. And these highly energetic electrons, what will happen to them? Some of them will also penetrate through them, and because they always follow the field lines. In the case of electron, they will follow the invert, opposite of the field line. Positive charges will follow the field lines, and electrons will follow the opposite direction, but along the field lines. So what will happen? Some of the electrons in the inversion layer, while reaching the drain, due to this two effects, one is the hot carrier and sometimes also avalanching, both together, the electron get multiplied also. Avalanching and hot carrier combined together sometimes. They cross over the oxide, reach the gate, and may again come back. But in this process, some of the electrons get trapped in the bulk traps of the oxide, or in interface traps of the oxide. The oxide is not an ideal oxide. There are many traps in the energy gap. Some of the there are more traps. There are more traps at the interface. There are fewer traps in the bulk. But these electrons, while going, they get trapped into that bulk traps or interface traps, and ultimately what happens? The threshold voltage changes. And if threshold voltage changes, the MOS will not function properly. This is what called a hot carrier induced trace. And I'll be discussing in the next lecture that a device called LDD, or lightly doped drain, is a very popular device to reduce the hot carrier effect. Hot carrier induced effect, which has become a very, very important constraint on ultra small MOSFETs. Earlier these things were not important. With shrinking geometry, these things are becoming important. And this hot carrier effect finally limit the performance of the device. To reduce its effect, we sometimes use a structure called lightly doped drain structure, which I think I will discuss in the next lecture.